Hello, hello. I'm so happy today to have Molly Morse, the co founder and CEO of Mango Materials, with us. And Molly, I'm always excited by PHA, and you're doing so much there. So thank you so much for joining us and teaching us more about PHA.
Sure. Happy to be here. Thank you.
Great. I know I've read a little bit about your growing up and the influences you had and that McDonald's story, but I want to still hear it. And I'm sure our listeners would like to hear, the influences that you had which led you to be where you are today. Let's start there.
Sure. So I had a bunch of influences when I was in elementary school. So probably like 8 to 10 years old that probably influence everybody, but where I am in my career right now, I can draw like straight lines back. And two that people often enjoy hearing because it has to do with garbage and waste and what have you is one, I went on a field trip to the Monterey Bay Aquarium, which is in California, USA, and it is like fairly well known in the space. And it was with my school, and there was this display of a fish tank full of these like styrofoam clamshells that were single use, like to put like a McDonald's hamburger in. This was years ago before they're packaged the way they are now. And it was, I can't remember the stat, but it was like, this is how many clamshells are discarded, every minute or what have you. And my like little elementary school mind was just blown. I could not believe how much waste there was and what a problem this could be if it improperly ended up in the ocean. Like I was like, oh right, like people litter and this could end up in the ocean. It could hurt the fish. And it just, that blew my mind. And then I also had someone who came into my second grade classroom who was talking about recycling and how we should recycle. And I think it was a huge push to get children to recycle, to go home and educate their parents. I think I was part of that and very successful with me because I went home and I was like the recycling police in my family. But it also made me, I built as like a small child a compost facility in our backyard, like totally attracted like rats and stuff. But that was my very, very beginning, being like, wow, all this stuff we put in our trash can, like, where does it go and what happens to it? And that's a thread that followed me actually through college, where I took a class on garbage or solid waste management, all the way to my career today, which is trying to address plastic pollution and find alternative solutions to the materials we use.
So, as somebody who grew up in India, and I might even make you jealous. And we lived for before my wife and I shifted to US. We lived on a mango and lychee orchard with at least 20 different varieties of mangoes, and I had to try every one of them every day. So the mango season was like 10 mangoes a day at least. So, so why did you choose Mango Materials? That's such a
Um,
cool name. So I wanted to know
yes,
where
so
it
I
came
would have been
about.
so jealous, and I would have needed to be your friend to come over and try every 10
Yeah,
mangoes every
we are, we,
day.
we are going there one day. We'll come to the farm to
Yes,
India
yes, I'm
together.
coming. Be right there. Hold one sec. um, So when we were incorporating the company, first off, we're me and my co-founders. We're very technical. I have a PhD in engineering. I have a very sort of technical company. We grow these bacteria called methanotrophs. We do gas fermentation. The product we produce is formulated polyhydroxyalkanone. It's super, super technical. So one of my co-founders was like, oh, we should call ourselves like Polyhydroxyalkanone Incorporated or whatever. I'm joking. And I was like, no, 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 no. I'm like, no, this needs to be simple. It needs to be approachable. We wanted to name the company after like a fruit or a tree or a plant, something natural sounding that was very approachable. And me and one of my co-founders, our favorite fruit is mango. And mango materials worked. We also weren't positive at the time if we were going to be focused just on like polymers versus like biocomposites. And so mango materials worked. We named the company after our favorite fruit. It was that simple.
And the
It has
packaging is
nothing
so
to do
good,
with mango.
right? No, but
It
the
has,
packaging is so good, right? The
yes,
leather, the mango leather is so cool.
yes,
And I was thinking,
yes.
it's just so. And of course, I'm constantly inspired by everything that nature
Yeah,
packages. But mango is a good one, right? The way
yeah,
it is structured and this, and how it protects the fleshy inside. So, but yeah,
exactly.
we are doing the mango trip sometime for
Yes,
sure.
yes.
But
And
let's go ahead.
mangoes are produced like consumed all around the world. I didn't realize this at the time, but it's a very approachable fruit because other fruits can be very local, but like pretty much everywhere I've been on the planet, people know mango. So they're like, yeah.
Now that you say it. Yeah,
Yeah.
maybe, but at least, yeah, at least most of
I
the
mean, it's
people.
not
I know
India
that
where they like
my
fall
wife
every.
grew up in West Virginia, and the first
Okay.
mango she tried was, I think she said 21. So maybe for the first 20 years she didn't know. Oh, she maybe
Yeah.
knew, but she didn't know what
Yeah,
it
she
tastes
she
like.
knew. It wasn't like, "Oh,
Yeah.
what is this
Yeah.
dragon fruit?" It
And
was
of
like, "Oh,
course,
no, I yeah.
her life changed since
Yeah.
then.
Yeah, there you go.
This is it. It's a pre-mango and a post-mango life.
Yep,
So
yep.
of course, now she's an aficionado, and then she loves the mango. Okay, so let's get into the civil and environmental engineering. Why? What drew you to that? And why that particular side of engineering?
Yeah, so, when I went to college, I thought I wanted to be a math major, and I was there for, like, 2 days, and I was like, "Oh, this is, like" I didn't realize math in college is, like, very, very theoretical, and I wanted to be very practical. So I talked to my college advisor and just explained what I was interested in, and he was like, "I think you might wanna be an engineer," and he had all these, like, brochures, and he was like, "Here you go," and I read the brochures. The first one I read was civil engineering, I was like, "Oh, yep, that's it. That's what I wanna do." Um, and so yeah, I've loved engineering all the time. I wasn't, and now there's tons of programs to expose high school students and whatever. I thought like engineering was for like boring. I don't know. But now I think it's a lot more well known. But yeah.
Yes, you remind me of a friend now, and he was on the show actually. It's a company, I don't know if you know them, Temper Pack. So
Oh
Peter
yeah.
Wells is a Scottish guy who's lived all over the world, but he's a civil engineer, and I love his brain because it's just structures and
Yep.
projects, and how do you
Yep.
do projects well, and
Yep.
how do you execute well, how do you build a structure well.
Yep.
So I think that
Yep.
also kind of gets well ingrained in your brain, right? When you're actually studying something like that. Does that make
Yeah.
sense?
Oh, for sure. And I think it's something I think about because I think I was trained for so long to think a certain way that it influences everything I do. I think it influences how I start a company. And it's just like, okay, we have a problem. What are the possible solutions and how do we get there? And I'm very like systematic about it. Even if it's like a people problem or like oh, someone didn't follow the correct standard operating procedure, SOP, in my company. Like, what can we do to fix it and make sure it's fixed next time? And let's have a procedure with a checklist. And I'm like that with pretty much everything. And I think it's because I was trained as an engineer.
It's a funny thought, but I was thinking, I want to see how she cuts mangoes. As you were saying, you're
Oh,
so
I'm still figuring
structured.
out the best way. And I'd love to just eat them. But yeah.
I'm going to get that one right too.
Yeah.
So tell me
Yes.
about meeting Allison and Anne.
Yep.
Right? I thought what I read was that it was during your PhD, and how did that spark fly, and how did you guys eventually decide that you want to do something together?
Yeah, going back on it, I think we were really, it was a fortunate accident that we ended up with the combination of co-founders that we did. Like when we were starting the company, I read a whole bunch of books and I knew that people problems are often what killed companies and fights with startup co-founders are incredibly common. So we knew the numbers, but we're so engineers. We're like, no, like what we do is really hard. We feed like gas to bacteria. Like how hard is that? If we're going to fail, it's going to be because we can't figure that out. So we knew this, but Anne, Allison and I, we were both PhD students together. We were in the same lab, working on the same project. So that's how I knew Allison. And then Anne and I met at an anaerobic digestion conference in Milwaukee, Wisconsin. A great place to meet co-founders. But we both just like loved our PhD work, which was linked, like similar, and actually her PhD advisor was related to my PhD advisor's advisor, like academically, not like biologically cousins. They're academic, like it was the same main advisor. And so we just like we loved talking about each other's work. Her PhD was on the production of methane. Mine was on the biodegradation of polymers to methane. So we just hit it off instantly. And we all graduated with our PhDs. And afterwards, I was looking at other companies in Silicon Valley start, and I realized that these other people were starting companies that sometimes they had no idea if the science worked. But we knew that theoretically, and we knew in the lab, you could go from pure perfect methane to PHA. We knew this was possible. So like if these people can start companies, like I can start a company. And so yeah, and so our the three of us all three of us have PhDs in engineering, and we have some similarities. And our research was all related but different. And now we all run different parts of Mango, and it's been many, many years. And let me tell you, I think there was an element of luck, and it was also an element of people that are going to go on a journey with you have some level of trust with each other because, yeah, here we are, and it's still working, and we still get along. So,
Yeah, that's amazing. It is serious luck. So when you were talking about anaerobic digestion, our CEO in India, the company I work with, is a very wise man. And I remember because I was like really butting in a lot in his work at one point. So one day he tells me, in a effluent treatment plant, there are two kinds of agitators: a stationary agitator and a moving agitator. So you have to realize I am the stationary agitator and you are the moving agitator. You only go where oxygen is needed. You don't
yep,
just turn up, where I don't need oxygen. So I thought that's such a great anecdote, and I've used it so much because and it
yep,
stayed in my mind that yeah, like if something doesn't need fixing, I can focus on other things rather than
yep, yep,
disturbing him and butting in and all sorts of
yep,
things. So that's funny. So why PHA? I know you said a little bit about methane and how it works,
yeah,
but as an engineer, you can get into many things, and PHA is one of those. And of course, I realize that you have an environmental side to you.
yep,
But
yep.
talk to me in detail. This one I want to know. Like
Sure.
what attracted you to this substance called PHA?
Yeah, so when I was doing my PhD work, I was looking at lots of different materials to make biocomposites. So you take natural fibers like hemp or jute or flax, and you smush it together with a glue type material to make a substitute for plywood. That was the goal. And so we looked at soybean oil based ones, cellulose acetate based ones, and looked at PHAs. So we purchased PHAs from others, and the PHA worked great. And it had great mechanical properties, and it had great wide-ranging biodegradability properties because it would biodegrade aerobically with oxygen and anaerobically without oxygen. And it would biodegrade, but it only would biodegrade if it had significant enzymatic attack. It needed a lot of bacteria. So if you had just it like on the wall of your house and your wall was dry and clean and no soil, it will last for ages. But if it's in the mud and moist, and then it will biodegrade as part of the naturally occurring carbon cycle. So that's what drew us to PHA. But we also had this joint project, and this is where my colleague Allison comes in and her advisor comes in, because PHAs are actually made by most living things on planet Earth. And most things on planet Earth have the ability to break them down as well. So PHA is a family of naturally occurring biopolyesters. There's lots of different types. And P3HB or poly3-hydroxybutyrate is one of the most wide ubiquitous ones, and the ability to break down that molecule is very common. And so at that time, early on, Craig Criddle, Allison's advisor and my co-advisor at Stanford University, was like, actually, this is very ubiquitous. Normally, the way PHAs have been commercialized is you take sugar, feed sugar to bacteria, they produce PHA. But he's like, I bet this pathway, it should be naturally occurring in methanotrophs. Like it should be there. And if methanotrophs could do this, then instead of sugar, we could use methane. And then we could wow, this would be amazing because there's methane everywhere around the planet as a potent greenhouse gas. If we could take methane and feed it to bacteria to produce PHA, that could be a game changer. So this was years ago, the beginning of Allison's PhD research. And yes, at Stanford, she proved out that you could take methane and produce PHA. And that's essentially all we knew when we started the company. Like we didn't know what high levels, what the properties were, would anyone pay for it? Would this be economical? Like we didn't know any of that, but that was the foundation. And that's why PHA can have great mechanical properties, can have wide-ranging biodegradability, whether it ends up in industrial controlled biodegradation environments or it ends up in the natural environment with significant microbial presence. It can enter the naturally occurring carbon cycle.
Yeah, I want to, of course, dig deeper into that one, but I want to just so that I've ticked off the boxes. You also get into, being something called Engineers for a Sustainable World, the
Yeah.
Unreasonable Group, and
Yeah,
then so let's talk about those two, and then I have a
for
particular
sure.
question after that.
Sure. Yeah, those are both part of my like extracurricular, like outside of school or work activities. Engineers for a Sustainable World was when I was in grad school. So believing that engineers can make the world a better place. It's sort of philosophically similar to Doctors Without Borders, like a little different, but people are often more familiar with that. But we did a lot of engineering projects that sometimes would involve sanitation, could involve drainage, which is like very sort of unsexy type things, but really, really important for humans. And then the unreasonable group is similar but different. This is like I'm still part of that now today. And the unreasonable group believes that in order to have like positive change in the world, you are reliant on unreasonable people who don't who see the world and see the need to make a change and like make it happen. And so it's the group that I'm part of. It's generally a group of founders who are tackling these big systemic problems. And we're part of a cohort that are just like, yeah, plastics are a problem and I'm going to solve it. And like, here we go. But then it goes back to like, to have that idea inside of you, you must be kind of an unreasonable person. So here I am.
Yeah, I would definitely. My people in our company will definitely fit me right there because as soon as they say, "Come on, try to be reasonable and
Yep.
practical," and I'm
Yep.
like, if you want me
Yep.
to reduce the plan, just say that. You don't have to use words like reasonable and practical. Just say we reduce the number. You're thinking
Yep.
to, and the other one, another funny one is my wife calls me a delusional optimist.
Oh,
So,
probably this is the same way, and it comes from a Bernard Shaw quote
uh-huh.
about like the unreasonable man. I think it's might be what it's called, but it's the same thing, but it's kind of a more it's a constructive way to say exactly that.
Yeah, it's something like, wasn't
Change,
that, yeah,
positive
change is
change in the
made
world.
by unreasonable people or something like that,
Yeah,
Or Steve Jobs also said something like that.
I
Yeah,
think there's a lot of it because there, Steve Jobs has, I think, the Misfits.
yeah, that's true.
That
That's true. That
yeah,
one is a
and there's
good
a
one.
thing about like black sheep, and yeah,
Uh-huh. Yeah,
but
yeah,
yeah,
we fit.
yeah, here we are. But I mean, that's also why sometimes maybe founders could be hard employees later on in life, or there's other things about
Yeah.
the
I
people.
would
But
I would never want to work for myself. I can assure you that. Why would somebody do that? Okay, why entrepreneurship? You are an engineer, you're well qualified. I'm sure, I'm unemployable, but you are employable. So, why would you go down this crazy journey of being an entrepreneur? Why did that bug bite you?
I wasn't really thinking about it at the time, like the long ramifications of it. I mean, I saw these people start, like I said, starting companies, and like I thought, as you said, like I was a technical person. I had a PhD in engineering. I thought that's what I was going to do, but I saw these people starting companies. I'm like, if they can do it, I can do it. And and that was really it. And yes, I've probably always been an unreasonable person, so probably working for myself, being like an inventor, entrepreneur, it was actually part of my like family as well. So I have a lot of family members and ancestors who created new technologies or started companies, and so I was like loosely familiar with that. And so when I think I had only thought I was going to be with Mango for probably like 2 years when we incorporated it. I thought it was going to be done, and here I am. It's been a labor of love, but yeah, it suits me. And now that I'm like much older, and I give a lot of talks to student groups, sort of in my free time as well, and see people make their own way. Looking back on it, I was like, oh, this is a perfect fit for me, the kind of person that I am, my risk profile, what I enjoy doing, what I get a thrill of. It's like a perfect match for just me as a person, which I think it's not for everybody. But yeah, that's why entrepreneurship. Yeah,
I
it's
was thinking you're probably going to say, now that I'm older, I'm wiser, and what was I thinking?
I think
But you and I
actually
know.
I think that because we have like sort of a fourth co-founder, Bill,
Uh-huh.
who has never worked full time with the company, but was very, very instrumental in the beginning and is still involved. And I've told him, I'm like, Bill, why didn't you tell me what I was getting myself into? I'm mad at you. And he's like, Molly, you would have never listened.
Yeah, it's like you never want to tell your friend that your boyfriend is not really the right person for you. It
Yeah.
never works, right?
No, no, don't say
That's
that.
like, this is your baby. You're now not going to
Yeah.
give it up. Okay, so I want to get into the weeds of it.
Okay.
I've, of course, I've had a few people on this show who work with BHA. Daniel Caraway is a very dear friend. I look up to him. Then Brad Rogers at
Yep.
Danimer
Yep. Yep.
again, and lots of other people as well who I know. And Sanjay at Chemira, who's again working with Danimer now. Like they're collaborating with dispersions. So I actually went and visited Daniel and saw his process, and it was all vegetable oil based, and
Yep.
I understood that. But I want to get into the understanding on how does it work with methane, and
Yep.
um, and how does it differ? Because
Yep.
Danimer is similar again to
Yep.
RWDC, and
Yep.
then of course I presume there'll be differences even in the product. But let's start first with the process on how it differs and how does the bacteria act, and then we get into the product. Does that sound okay?
Yeah, for sure. So the full-on fermentation process to produce PHA powder is, well, actually, to get PHA in the cell, I would say, is completely 100% different. Like you could gift me the equipment that either of those companies use, and we couldn't do anything with it. Our bacteria are gas eaters; they eat gas. So our fermentation is completely different. Our bacteria live in these deep, tall tanks where gas comes in. We need both methane and oxygen. Both those are the two key items that our bacteria need, and without them, they will not grow. So, delivering gas is a thermodynamic endeavor and the most critical thing to our organism, which means that the fermentation is just drastically different than if you're feeding some kind of oil or sugar that's either a liquid or a solid. It's completely different. Then these are gas eaters. The bacteria themselves are different. Their cell walls are different. However, at the end of the day, the molecule that they produce inside could be very, very darn similar, if not identical. So the metabolic pathway inside the organism that's the reason the bacteria are producing this is in case there's a time of famine and in case there's a time of carbon limitation, you induce the bacteria to produce high levels of PHA so they can store carbon inside their cell walls. That's what PHA is. And so the reason that happens is similar in the bacteria, I would imagine. And there's different limitations and there's different stressors you could put on the bacteria that are probably similar that would induce this PHA production inside their cell walls. So there's probably some similar biochemistry going on in terms of the stressor, but the actual pathway is going to be different. Like in us, it goes methane, methanol, formaldehyde, and you go through these different pathways in the organism that's going to be different. However, if your bacteria like ours is producing P3HB, there might be, it is possible there could be something about the stereochemistry that's different, and there could be something about the molecular weight that's different, but really, once you have it in the cell wall, you have to get the PHA out because you don't want the biomass. So once you have that situation, there's our cell walls are different, methanotroph cell walls are different than others. But once you have that, there's going to be a number of similarities to isolate that PHA granule, to clean it, to rinse it, to dry it, to purify it. Those steps most likely could be very similar between the companies, although they would be different just because I know the methanotroph cell walls are different. So, if you have a certain technique that like you engineered your organism to excrete the PHA granule, if you have lots of little granules, that's going to be different than if you have a big one. And then if you have a lot of little ones, how like and I'm getting super technical here, but how like the protein sheath like adheres to the granule, all that could be different from the organism. So that means you would need slightly different cleanup steps, but we will all need cleanup steps. So if I was gifted that equipment, I could most likely use it or augment it to work for our process. So the key difference is upstream, completely different. And Mega Materials is also dealing with a flammable gas mixture, methane and oxygen. So, but I'm sure they have they probably have problems with needing to store their feedstock, or everything loves sugar, so they could have invaders, and they could have like contamination with their feedstock. I'm sure they have other problems, but we have an explosive gas mixture, and we need to dissolve the methane, the gas, into solution. So that's our key challenge, which they would probably, yeah, our company's technology is completely different there.
And when we look at the base bacteria itself, what was it like to find? Because you say that the bacteria itself is different because it's a gas eater.
Completely.
So how does one go about finding and reproducing the bacteria? Because I presume you need a lot of the bacteria, the
Yep.
cells, to be able
Yep.
to put them into the system. That's the first part. And the second is, what I basically saw was big tanks, right?
Yep.
Ultimately. So is
Similar.
it
Yep.
still kind of similar? It's just different kinds of tanks. So
Yep.
yeah, those two
It
things would be great as well.
Exactly. So it's probably similar. We both have a bunch of big tanks, and we probably have different probes, and we have pumps around the tanks. Like there's probably a bunch of stuff that would look very similar. Um, but the bacteria themselves will be completely different. Our bacteria are isolated from the environment, so it's important to find high PHA producers, but what really becomes important is propagating them to control, if the bacteria double every few hours, over years and years, propagating the best bacteria that can produce high levels of PHA the fastest. That's generally what we're focused on, and doing sort of self-sorting to select for the best. That's really core to us. And actually, that process could be quite different between companies, because it is possible others are just taking a model organism and engineering it to do this. So that whole process could be completely different between technologies as well.
So it's basically like we do in cellular multiplication, like in tissue culture, and you
Yep,
select the best, and then you
exactly.
multiply that,
Yep,
and you just give it the right environment to be able to
yep,
multiply. Is that how it'll
yep.
happen?
Very, very similar. Yeah, our bacteria are a little different because they don't like to grow on plates. They can, but they don't like to. So it's yes, but theoretically, like yes, exactly that.
And would you say if you look at just the process of using a vegetable oil or a sugar, starch, and feeding it as a process, does yours with the inflammability and a gas, does it become more difficult or does it have its advantages? Just isolating the process side of it.
Yeah, so I'm no expert on like sugar or vegetable oil or whatever fermentation, but I think there's pros and cons to each one. So yes, we have the flammability. That's the I'd say flammability is number one, something that we have to address. That's an engineering challenge. It's not the end of the world. A ton of processes use flammable or poisonous or like toxic, all sorts of crazy stuff. We have a flammable gas. We need to manage it. It's critical to our technology and our company. Safety is number one. Don't mess with that. Number two is thermodynamics. We have a gas that we need to dissolve in solution for the bacteria to eat. So those two things are unique to mango and will be very different. However, we have this very wide ranging feedstock that is all over the planet. Our bacteria can handle very sort of dirty gas. So if there's other things in the methane, our bacteria can handle that. It doesn't make our bacteria sick. It might corrode your equipment, but it doesn't make the bacteria sick. Um, and not only that, this carbon feedstock is essentially, it's everywhere. It's ubiquitous. You don't need to clean it up. You don't need to go out to the farm and collect it and put it through a whole bunch of processes to get the feedstock you're feeding your bacteria. Um, Not a lot of things. Well, there are a lot of organisms on planet Earth that can eat methane, but it's not like you and I don't want to eat methane. Whereas something like sugar, you and I love myself a mango. I would, and like a lot of things on planet Earth love to eat sugar. So you have a couple other things if you're using that sort of feedstock. First off, you might have sterility problems. You might have invaders or other things in your tank that accidentally take over and you're growing the wrong thing, not the type of bacteria that make PHA. Also, you might have concerns depending on what your feedstock is that maybe that agricultural land could have been used for plants for human food consumption or for something else, and instead we're making it our um, for our material that's going to go into our sunglasses, or something like a little more, like it's not like just food to survive. So yeah, so there's pros and cons for each. I mean, we're a huge believer of methane and the C1 platform. and believe that this is the feedstock of the future. And we're going to have these biorefineries all over the world where everyone can use methane to make the different materials. Like, this is our big dream, but there's a huge need for PHA and other materials. And it's great to have lots of routes to get there. So yeah,
Yeah,
we're pro methane fermentation, but
and more
you know,
power to you. Let's hope you create lots of it and keep succeeding with that. Just on the product side, you kind of mentioned PH3B. Is that what you
yeah,
called your structure?
yeah,
So in terms of the molecular structure
yeah,
as well, I've heard of PHB, PHBV,
yeah,
PHA, and of course,
yeah,
this, I presume it's different molecular lengths.
yeah,
And how do these differ? And
yeah,
why do you choose a particular structure? And how
yeah,
does that help the product side? Or is that just
sure,
something that comes from this process?
yeah,
Enlighten
for sure,
us on that.
sure. So I generally refer to what we do as PHA, but PHA is the family. It's like, but there's many, many types of PHA. So there's P3HB or PHB, you could call it either one. That's what our bacteria naturally produce. But then there's also PHBV, like you mentioned, PHB-HHx. There's lots and lots of different types in the PHA family. So PHA just means polyhydroxyalkanoate. So this is this whole family of polyesters. And so they all have sort of similar structures, but if you have P3HB versus P4HB or versus PHBV, hydroxyvalerate, or HHX hydroxyhexanoate, you're going to have slightly different molecular structures and you're going to have slightly different properties. It's going to melt a little differently. It's going to have a little bit different mechanical properties. It's going to have a little bit different biodegradability properties. So it depends on what the structure is. So the reason we produce P3HB is because it's what our bacteria naturally do. So there's nothing, there's no like genetic jockeying that we do for this to happen. It's naturally occurring. And yes, we've controlled these environments to get the very high producers as the organism that we use, but this is naturally occurring. So in our case, we have our bacteria produce high levels of P3HB. And some people might say, oh, it's a little brittle or what have you. And wait, first off, there's a lot of things you can do once you have the PHA inside your cell walls and you need to clean it. A lot of those processes can actually influence your like it can kill your molecular weight, or it can augment the properties. Every time you kind of heat and cool, it's possible something's happening. But what we try and do is have very high levels of P3HB, and then we formulate the material. So we'll add a little bit of, depending, I mean, maybe we won't, you can use it straight for some applications, but for a lot of applications, we formulate it to add maybe a tiny bit of nucleating agent, a tiny bit of plasticizer, or something to augment the P3HB properties so that it can melt and flow and have the mechanical properties that end customer desires. Now, it is possible, instead of doing that, to engineer your organism to change the format of PHA to have better melt characteristics or to have different mechanical characteristics. So maybe you want something that's more ductile than P3HB. You could engineer something in the organism to have those unique properties. So there are a number of companies. Mango doesn't do that. We're just like, our organism does P3HB. That's all we're doing, and produce really high levels, really pure, do it again and again and again, and then formulate it afterwards. That's what we do. But others could engineer the organism, and that's super cool because then you have the exact molecule you want. But then you have to do all the microbiology and what have you. So it's just sort of, it's like artists. It's a different vision, a different approach. We like ours. And hey, because we produce P3HB, if we blend it or add it to a different form of PHA with different characteristics, that might give you the perfect material for a specific application. So we'll purchase PHA from others. And some people, you might think like, oh my gosh, is that your competitor? I was like, well, we want to produce P3HB and there's different reasons to have others. So we'll purchase it from others to get the perfect formulated pellet for somebody else. So yeah, so anyway, the PHA family is really amazing. Like, you can totally go down a rabbit hole, which we don't. We're just doing P3HB, but you can, like, HHX, you can get these long side chains, and you can get really, really unique properties. And that's also going back to like one of your very first questions. That's why PHA as a family can replace pretty much all plastics on planet Earth. You can get really ductile, flexible, you can get rigid, you can get good tensile properties. Like um, through engineering or augmenting through the PHA family, you can replace like the vast majority of plastics we use, and so that's why.
Yeah, and I know a lot of people like I'm sure you know CJ Biomaterials and
Yep.
NatureWorks, and both of
Yep.
them again have been talking to, and they are blending PLA and PHA.
Yep.
So
Yep.
again,
Same thing.
and you said brittle in case of P3HB, but of course PLA is brittle, and then
Yep.
they're adding some PHA to make it less
Yep.
brittle. So so
Yep.
that's a different structure they're making. So it's just interesting what you're saying that
Yep.
it depends on what you want, and then you can
Yep.
create one. You can come from your Puritan, via P3HB, and then yes, we can pick up materials and create different substrates again. What about productivity? When you look at productivity vis-a-vis a different production system, how does it differ? Like I don't know how would you measure it as well per ton of material, or I don't know.
Yeah.
Like again, I'd love to learn how do you see productivity, because it will link to my next part, which is cost, right? So because again, those two things vis-a-vis, again, maybe vegetable oil or starch or whatever, how do
Yeah.
you see it?
Yeah, so if you look in like the academic literature, people love to be like, "Oh, what's the doubling time of your bacteria?" Or "What's the percent PHA cell mass? Like, can you get like 90% of your cell to be a PHA granule?" Or "What's the grams per liter per hour of PHA that you can produce?" So it's like grams of PHA per liter of fermentation broth per unit time. Like people get really fixated on all these things, and I think it's cool. I love to see like the general trends and all that, but at the end of the day, what really matters to us is like how much feedstock do you have coming in? How much methane or sugar if we're comparing it? And then at the end, how much powder or really formulated pellets, but like how much powder do you have coming out? And actually where what we found is like a lot of the areas to optimize, people love to get into like the organism and the genetic engineering and how do we fix that? But you know what? If you have a process where you're trying to you're trying to isolate your PHA granule from the water and you're trying to dry it, and it turns out like that system isn't very efficient and like powder's falling out and going down your drain into your waste. Like we through our like mass balance analysis, we realized that like that's where we're losing a lot of it. It's in the downstream processing steps, like separating out the water, cleaning it, purifying it, drying it. And so we try and look at just grams or liters of feedstock coming in. So like gas coming in and like PHA going out. And so the other way to compare it is also just looking at the stoichiometry of how you take methane and convert it within the organism to the PHA molecule. So you can look at how much carbon you need for um, how much carbon you need in your feedstock to how much carbon you get in your um, PHA molecule. And actually, that's why we love gas fermentation is because it's so low cost. Like the amount of, this gets to your next question though, is you really need to get scale to enjoy that. But if we were to make 1 billion pounds of methane based PHA powder, you're no way can you beat the price of the methane molecule paying for that compared to something like sugar or a different feedstock. If you want 1 billion pounds of low cost PHA powder, you need to use methane as your feedstock because that's the way to drop the cost. However, we need to be at those big scales and we need to get there for that to be our biggest cost factor.
Yeah, yeah. And but would you call it like uh, yield in terms of usage in this? Like because I've heard of all sorts
Yeah.
of numbers, right? Like 80% getting converted, like you were saying, what is the
Yeah. So
molecular weight,
probably like
and
the
down to
80.
30% as well, so
Yeah,
I
exactly.
don't
So
know.
if you're talking about something that's like 30 to 90%, it's probably the percent PHA cell mass,
Yeah.
the weight of the PHA compared to the weight of the overall cell mass.
What
That's
came
probably what
in?
they're
Yeah,
looking at.
maybe.
Same the yield. Yeah, you're probably looking at like grams per liter. Yeah, and people get like really into this.
Yeah, very, very, very geeky.
Um,
And
Yeah, I want low amount of feedstock I'm paying for, and I want on spec, on price point, PHA powder, or really ideally pellets, but that's a lot more straightforward engineering going from the powder to the pellets. I mean, there's a lot of art there, but in terms of losses and cost, it's more straightforward. Yeah, I like to look at the overall process. But yeah, especially in and that's actually one thing that's unique about PHA is like all the academic work. Yeah, they get really into that, which is cool. Like, yes, all that work should happen, and we will read all the papers and learn from it. But yeah, let's make sure your PhD.
What about homogeneity when you look at a gas-based production? Do you get it pretty like you said, you in a way you're a Puritan
Yeah,
P3HB,
yeah,
so is that also because it's quite homogeneous, or do you still have to,
yes.
it's just the
So
way the process works?
exactly. So our bacteria will only eat methane and will only produce B3HB. So other technologies will be different. Other ways to do this will be different. But if we dumped tons of sugar into our tank, um, like maybe something else would eat the sugar, but like we're creating an environment where you have to eat methane to survive. There's not contamination. That's the only thing they will do. So you can't feed them another carbon source.
You don't want to
They
give them indigestion.
no. But so other organisms, if you change the carbon feedstock, you change like the number of chains in the carbon feedstock, it might change the PHA structure. Um, Not for us, but for others, I think that's possible. And so then it's like, oh, we have a different carbon feedstock. Now we're getting a different product, or slightly different product. That doesn't happen to us.
And you said it's relatively easy to, I know that's relatively easy to get oxygen, but you said methane is also abundantly available. So do you have to
Yep.
actually buy methane, generate
Yep.
methane?
Yep.
How does it work? You just get it in tanks and feed it? Is that how
So
it works?
we're actually currently co-located with the methane producer. So we actually have an
Super.
agreement with the municipality, and we have been located on sites where the methane is produced. So that is a limitation in the future. Our hope would be you could just be located anywhere on a natural gas pipeline. But yes, we pay for the methane, and we are located where the methane is. We do not tank it or ship it. We do ship the PHA pellets, but we are converting that gas into a solid on site where the waste methane is.
Yeah, and any sewage plant or even a
Landfill.
landfill, they would all be
Yep.
generating methane,
Agricultural
right? Agricultural
facility,
methane, animal
coal mine.
husbandry. Yeah. Oh, coal
Yeah.
mine as well.
Yeah.
Wow. Oh, yeah. There's a lot of places you could be
Yep.
co-located for sure,
Yep. Yep. I
and they
mean,
would be happy to get the methane used. We
yep.
we we have a sugarcane-based pulping plant, and from the wastewater we create methane, which we take to our boilers.
Yep.
So we
Yep.
just burn it. But I wish,
Exactly.
that I wish someday we will produce PHA
Yep.
with you, or
Yep.
P3HB with you.
Yep. Yep.
So what about why? So I see that you've gone for mostly textile as a usage. What is that? Why did that happen? Why did you choose this particular
Oh,
line of usage?
well, you're probably seeing that because that's what's gotten a lot of press. But in terms of
Ah,
actually volumes of material produced, it's actually more on the injection molded side. Um, but so fiber, whether it's for nonwovens like wipes or fiber for things like apparel, huge volume, huge need to change the way the material is produced, and also for like things like apparel, what happens end of life. And so sure, like we should recycle that all, but if we have microfiber shedding, if it ends up in areas without modern waste infrastructure, we want those materials to be able to go into the naturally occurring carbon cycle. And so fashion fibers is a huge volume, huge need for environmental change. So the work that we've done on that front, yeah, I actually have a shoe upper right here, but yeah, I have like injection molded. This is
love it.
back scratcher. But the work that we've done on fiber has gotten a lot of press. So fiber is tricky. Like this is like a shoe upper made out of
Beautiful. Yes,
PHA
nice.
based
And
fiber.
it's
So
totally PHA, as in the non-woven structure is like
yes,
it
that
is going
that
to
one.
biodegrade eventually.
Yep, that one is. Sometimes there'll be others where maybe you have like PHA fibers in one direction and like cotton in the other or something, just to like because we're limited on how much PHA we can produce, and we don't produce fibers. We our company only produces formulated pellets. Someone else takes the pellets and melts them to make fibers. Then someone else will take the fibers and knit them to make something like a shoe upper or something else. And so getting PHA that has those melt flow characteristics that you can come out of the spinneret and you don't have strand breaks and you have the uniform melt, and then getting the material that's strong enough that it can go through a knitting machine. Technically using PHA, that's super, super, super tricky. It's really hard. It's amazing. And like we knew that this was possible like years ago, and now we've proven out that it is possible. And that's why that work's gotten a lot of press. But that item isn't currently on the market. Like what is on the market is all injection molded. So this is either emblems or little other items, cosmetic packaging. So Natura, the Brazilian cosmetic company, I don't think I have any of their stuff here, but they have a soap dish. So it was melted down by a company called Silgan. Silgan injection molds these soap dishes, and the soap dishes are sold in stores and online by Natura. So that those are those sorts of applications or toys or other items are the ones that actually have we've like shipped more volume of pellets, and those are the ones that are fully commercialized. But fiber is super cool and sort of the long-term North Star, because if we want these if we're going to have 1 billion pounds of PHA, we're going to need a lot of volume, and fiber is a way to get there.
And you've used this term a few times now, pellet and powder. And you've
Yeah.
used it also that it's difficult to create pellet from powder. So when you are actually when the PHA is being created,
Yep.
what I've gotten so far is that it's like in a powder form, and then you pelletize
Yep.
it. Is that how it works? Or what is the process, and why is it difficult to make it into a pellet?
Yeah, so it's actually not super difficult to make it into a pellet. It depends what you want your pellet to do. But when it's a granule inside the organism, and then you have to separate out the cell mass and clean and dry and isolate that granule. And so at the end of that process, you end up something with like a white fluffy powder. It kind of looks like flour or something like that. And so and you could just ship that. So some PHA companies, that's their product, and they ship that white fluffy powder. However, what Mango does is we formulate. So we take that white fluffy powder and we take those other key ingredients, and what we ship are pellets. So it looks like this. And so it is possible that you just take the PHA powder and you densify it to make pellets. That's possible. Nothing's added. Or you might add just a little something to help with the melt flow, help something with the strength. And in that case, you're shipping the pellets. So what we do is we produce different pellets. And I like to compare it to dough. So like you can have dough that has like flour and oil and water in it. You can have dough for pasta, or you could have dough for waffles, but it still has the same kind of ingredients in it, just different ratios. Same thing at Mango Materials. We produce pellets, but we have a different formula for fiber and a slightly different formula for injection molding. So that's like our pasta and our waffle. And so if you want to do fiber extrusion, you have to have it's similar to having pasta. You need to have the perfect recipe, because if you put your waffle dough into your pasta machine, you're probably not going to get pasta. So that's why it's really, really critical to have the perfect recipe if you're doing something like fiber. Something like if you're making a waffle, got a little more variability. It might have a couple holes in it, but you can still eat it.
Yeah, like an Italian would appreciate this last part of your explanation. Because you have to have the real dough for the real pasta.
Yes. Yes.
So you've again talked a lot about extrusion, for example. A lot of the formulation needs dispersion, and what I'm told is that it's a little more difficult to disperse PHA. And why is that? You know, extrusion, sure, I understand. You create a good pellet, and it has a good met flow index, and it extrudes.
Yeah.
And
Yeah.
and what is the challenge with dispersion? Why it doesn't blend well with water? What happens there?
I know. So we're actually doing no work on dispersion. We're really focused on injection molding, and then some fiber and some film. I don't know I mean, I know there's a lot of cool stuff going on at the research level, looking at dispersions, looking at coatings, looking at like even like latex like properties. So I know that it's possible. I think in terms of just application development and your go-to-market strategy, um, it's most straightforward. That would be my guess as to why we're all focused elsewhere.
Yeah, yeah, I get it. So you have a thing for cool names. The other cool name I found was YOP. You
Oh, yep,
oust, and I was like, YOP and YOP
yep,
plus. You
yep,
oust
yep, yep.
polluting plastic. I was like, huh,
Yes,
it's that simple, huh?
yep.
So tell us more about the namification process. And then, of course, what is YOP and YOP plus? What
Yeah,
are the
sure.
differences
So,
there?
we were trying like so what we make is formulated PHA. Like generally, you can't have pellets that are nothing but PHA, but even then PHA is a family. There's P3HB and there's PHBV and a whole bunch of others. Like, oh my gosh, that's really confusing for the customer that like they're not really exactly the same, but they're the same family. And if you're going to compare PHB and PHBV to like polypropylene, like these two are in the same family. So we were trying to come up with a way that we could talk to our like a lot of the customers that talk to us are the end brand user. Like who the real customers, like who Mango ships to is the milk processor. So kind of like that example with Natura, like who we ship to is Silgan, a milk processor that like unless you're in like injection molding plastics, you probably haven't heard of. Um, Most people like you may have not heard of Natura because they're very focused in South America, but like they've historically owned other brands. They own Avon right now, so Americans often have heard of Avon. They used to own like the Body Shop and Aesop. These are other global brands. So people will be like, "Oh yeah, I know Body Shop," or "I know," like historically they owned those. And so, but it's like the Naturas of the world that have been coming to Mango to ask for the material, even though they don't buy pellets. It's their supply chain partner. So we've been trying to come up with a way that makes it easy to explain what we do. And then also it gets very complicated very quickly because we also our feedstock is that waste methane feedstock. But if we're using other forms of PHA, they might not have that same carbon negative story because methane is often a waste greenhouse gas. Like the methane we're using right now, it would be flared if we didn't feed it to our bacteria. And so some of our brands, especially in like the fashion type space, very much care about that. They want to be able to tell their customers this is from waste methane emissions. But then it's like there's also a benefit just from it being PHA, even if it was from sugar fermentation. So that's why we have YOP and YOP plus. So the YOP plus is the climate positive. It's the methane based PHA. YOP can be any form of PHA. It could be methane based, but not guaranteed. It could be plant based. So that's why we have YOP and YOP plus. And YOP is just a synonym for formulated PHA. And then the reason YOP is because we were trying to come up with a way that like the consumer has a choice. You are making a decision. And when you can choose a material, you can choose a material for the environment. So that's why we called it YOP for like you oust or to get rid of polluting plastics. Like, yeah, trying to put like make a vote with your wallet for the environment, like when that time comes.
Yeah, you've clearly learned the art of marketing as well, then, right? You're making
Oh,
the
that's
customer
a lesson. I'm an
the
engineer by
center.
training. It doesn't come natural yet. We're
Front,
working on it. We're
yeah,
working on it.
front and center, the customer. That's my wife comes from the communication side, and she's
Uh,
always like, "It's not about you, dude. It's about the customer.
yeah,
You don't have to talk about yourself and how cool you are. You know,
yeah,
you have to make sure that the customer feels cool about using your
yeah,
material, right? And that's
yeah,
exactly
yep.
what you're doing. So, what has it been like the customer journey? And tell me more on the difficult bits, right? Everybody will say, "Oh, my customers are great," and everybody wants to accept it. And so what are the difficulties there in convincing customers and doing the trials with them? And what has that been like?
Well, I would say two things can be true, both of those at the same time. So our customers can be great and I can be thrilled to have them. And at the same time, oh, there's so many different things. The PHA melts and flows differently, and most of the groups we're sending it to, almost always, very very few exceptions, it's the first time they've ever used PHA. And so if you're working with a group that's been melting the same polymer for the last 70 years and you send them something different with instructions, hopefully in their local language, to be like, hey, this melts and flows differently. This is the way the temperatures work. And they're like, psh, I've been melting polymers for 70 years. I'm going to do it this way. I can guarantee you they probably won't be happy if they don't change the temperatures. But then it's like, this is your customer and they didn't follow instructions. So maybe they like smoked out the machine and you're like, yeah, oh, we told you like not to melt it at that temperature. So, yeah, like in everything in between, like, I mean, the saddest conversations I probably have, like if we're gonna be like, oh, what's really hard is like I've had a lot of big plastic users who are like, yeah, we know PHA will work. There's not enough pressure yet. Like we know you're very cost sensitive right now because you're small, and yeah, like we know that it'll work for us, but there's not legislation and there's just not enough pressure, so we're just gonna wait. And like I've had a number of those conversations, just like, oh my god, you guys produce billions and billions of pounds, and you also have like the profit and the revenue and everything, and you put like billions of dollars into advertising or something, like a couple million here would make a huge difference in this industry. Those conversations are like the most depressing ones. But for those, there's a lot that are like who've been, working, adopting new products. Yeah, but it's like, I mean, it's fun because it's very global. We ship all over the world. Oh yeah, different like this is so something I didn't realize I'd have to know anything about, but getting stuff stuck in different ports around the world. Like, oh my god, why are these thoughts in my mind? But it's like, oh seriously, you need the outside of the pallet in millimeters, not the like inside of the actual box
Inches.
on the pallet. Oh my god.
Things you didn't think that you would have to learn in
Yeah.
business, right? There's so many variables that come
Yeah.
in, and then there is the legislation in different countries and regulations and all of that
Oh
too. So
yeah.
what has it been in terms of funding? There's a biomade investment that you have, but
Yeah.
how easy or challenging has that founder's journey been to kind of get the amount of money that you need and keep things afloat, not have sleepless nights? What has that journey been like?
Well, I always joke that like we have so much going on. I'm so at capacity that I sleep really well at night. But
I'm dead to the world.
yes, pretty much. I'm like, okay, off. Um, I mean, it has happened a couple times in the duration of Mango. I mean, so funding's always been challenging. I mean, it's always been challenging, and here I am, still in business, money in the bank with my team. But those two things are true. It's hard, and people always think like, "Oh, you're in Silicon Valley. There's so much money." It's like, yeah, yes, and we're total like the weirdos building a factory at the wastewater treatment plant with infrastructure and pipes and tall tanks, and people come and visit us and like, "Oh my gosh, you have stuff, and you're growing bacteria." And yeah, so like our first funding was from the National Science Foundation. It was a SBIR grant, Small Business Innovation and Research. It was 150,000 US dollars. Me and my co-founders, we thought we had won the lottery. We thought this 150K was like more money. It was for 6 months worth of work. We thought it was like so much money. We were so excited. And that led to like a phase two and all this other money from NSF. And then we got money from NASA. And yes, we have the Biomade project contract. And a whole slew of others. We also have done a number of rounds of equity investments, so selling shares of the company to get us what we need. And it's all worked. Here we are. Yeah, super proud of where we've been. It's also been really, really, really hard. Like, yeah, for all those grants and projects and contracts that are publicly announced, there was other things we applied for that we put our whole heart and soul into and we didn't get. And yes, we have great investors. I love our board. But for all that money that came in was tons of people that told me like, oh, I don't think anyone really cares about the environment. This was early on, or like something else, so there are a lot of no's. There's a lot of rejection. I think just going back to the whole entrepreneurship journey, it doesn't get to me as much as it gets to other people. It still gets to me, like just hearing no, 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 no all day when you really need the money, and yes, that can be a downer. But but it has all worked out. I have great partners. So yeah, but yeah, it's like sometimes when I talk to other people, like if things are hard, I'm like, this is happening, this is happening, this is happening. People are like, oh my God, if I were you, I'd be like dead right now. Um,
And
so
have you managed to dilute to the level that you would have liked to, or have you had to dilute more than you would have liked to?
as time has gone on, I'm happy and proud of the amount I've been diluted. I mean, I needed that money to get to the next stage. There was no other option. Um, and I try to actually pick my investors very carefully. Like if we're going to be wildly successful, who else would be making tons of money and where is that money going to go? Um, and so yeah, I'm like I'm fine. It like made sense. I did what I needed to do. I much rather have a smaller piece of a very, very big pie than one tiny pie to eat myself. And like for
Yeah.
me, going back to my co-founders again, I think this was something just accidental that we're all on this journey together. And yes, I want to make a lot of money when Mango Materials exits, but it's also about the journey and doing it with like the intention in the group that you love and is meaningful and trying to share in all of that. Um, and really firmly believe that you can change the plastics industry for the better. Like that's really what it's about. And yes, I'm going to make sure I'm protected and have as much equity ownership as I can, but at the end of the day, a couple of percentages here and there to get to the next scale that you really need to, that's really what's critical. But it's been really hard.
Yeah, that's the part which most founders talk about, and like it's so tough to actually get the right investors and get the money when you need it, not when
And
you, yeah, when you
the other
really
thing is
really want to.
a lot of
Sure.
a lot of things can change and they can change in the 11th hour. So if you're pushed into an exit at an unexpected time, that's often I think when things happen. So I don't have that on the horizon at all, but I think that when I've heard and learned of stories like that, it's like you can really get pinched then. So right now I'm in a great situation and I hope we'll have a very successful exit and I'll be poised to architect it in a way that is beneficial for all parties. But I think sometimes that happens to founders and I think it can be real when that does happen and things go bad and you get pushed down in the exit, that can be really hard. And it just hasn't happened to me yet.
And what is the arrangement with it's called Vacaville City? It's
Oh yeah.
is that
City of
where you're kind of using their methane? Is that what it
Yeah.
is? What is that
Yeah,
about?
so, within the past year, we moved to the city of Vacaville. It's in California, sort of outside of Sacramento. And so it's been an amazing location for us. We love the city council. We love the whole city. They really firmly believe that biomanufacturing is the future, that that's where new green local jobs could be created. That's why we moved there, by the way. They have a wastewater treatment plant where they have anaerobic digesters where they produce a lot of methane. So now we have exclusive rights to that methane. They also have land surrounding it that's not like in the middle of the city, it's further out. So it's a great location to have a PHA production facility. So it was essentially our dream location. It's been wonderful. We're thrilled to be there. We're working through like design review right now. So fingers crossed for us to get this all going, but they've been great.
So when I was 16, I went to an all boys school, and this was my prayer to the good Lord up there that may I be surrounded by beautiful women. And I have three beautiful daughters. I have a wife, I have a mother, and I have two girl dogs. Seven beautiful women around me, and it all came true. And you lead it. So tell me a little more about you talk about being in a women-led company, and tell me a little more, tell us a little more about that journey. And it is a proud thing for me as a true blue feminist. It's definitely
Yeah.
a proud thing. I wish I could have more women in our board and in our leadership team, but
Yeah.
we keep faltering. So give me, actually educate me on how to do that, how to find the right women to especially in leadership, because with all the best intent, I fail. And I would
Yes.
love to learn from you. How do I find the right women to be in leadership and on our board? Of course,
You
across the
know,
company, yes, it's easier.
it's the same thing. Going back to finding my founders, it was just kind of an accident. Like, so I'm actually the opposite of you. Like, I'm married to my husband, a man, and I only have boys. And actually, historically, educational wise, from actually, so when I was in high school, I had lots of friends that were girls and who were super smart. But then when I went to college, I was like, oh my God, there's so many boys. Like all my classes were like predominantly male. And that actually was all the way from beginning of university, college up until through grad school, predominantly men. So Anne and Allison, I think all kind of bonded, like kind of like we all had, I'm still friends with a lot of the boys, men from those parts of my life from undergrad and grad school. So lots of them were great, but there is something different probably about being a girl. And so I think we bonded because of that. We became friends. I think going back to being co-founders and having this level of trust, we felt like we understood each other in a different kind of way. Like, would this have happened if Allison or Anne were a man? Like, probably. And I think it would have been fine. Like, I had a lot of really close friends in grad school that were men. Um, and so I think the reason we ended, I mean, going back to kind of like when I was young and growing up, like I think there was a lot of unique factors in that situation for me personally, like, and also for Anne and Allison as well. The one thing I will say that like sometimes I think I'm like, this would be an interesting like sociological like exercise is how the three of us like ended up where we are. And the one thing I will say that you're going to be like, seriously, this is where you're going. All three of us had moms and dads who were married who had very equal type marriages and careers. So we all like in my family, like both my parents worked, they actually worked together, but my mom was like kind of the boss. Like that was just kind of I think it was like a stereotypical like Irish Catholic type thing my mom had going on, even though my dad wasn't at all Irish Catholic. But like there was this thing where it's like like ask your mom, she's the boss. Like that's like kind of how it went. But it was like a very loving relationship that my parents had, and same with Anne and Allison's parents, who I don't know like intimately like that, but they're both Anne and Allison's parents are still alive, still married, still like happily together, and they have that balance. So I think there was something about that growing up that was unconscious that we had, that you have this partnership, that you work together, that somehow Anne and Allison and I have managed to replicate as leaders of a company, that we each have like our own area that we focus on, but we back each other up when the time comes. And then you have those sorts of factors, your parents and your family. I was actually the oldest, or I am the oldest of three kids. I have a younger brother and a younger sister. Allison has one older brother, and Anne's an only child. So I think that comes into this as well. And then also we all I played sports very competitively growing up. I loved that. I was like super, super into like, well, first off, monitoring everything about my health so that I could win and be the best athlete and whatever. But I think going into women leadership type things, having that competitive sports leadership type thing. And yeah, so in most of those situations for me, it was like girls' teams. Um, I always went to co-ed schools, but there was probably something about that fosters a certain unique type of collaborative leadership. And I do think, and this is maybe a little controversial, I do think women lead differently than men. I think, and so many people at this point have come to me now, and when they visit Minka, they're like, whoa, 3 women bosses. This is refreshing. Like refreshing is the word that they often use. And like people would just be like, this is different. Yep, you guys are really different. And like, I don't really know what it is because we've been doing this together for so long, but they're like, yeah, you're different. And like, I think there's something gendered there. But it works for us. And we are in a very male dominated industry. Most venture capital dollars go to men, but most biomanufacturing companies are led by men. So I don't know. So I have Anne and Allison. Yeah, I have all boys in my house. I don't know. I don't know. We have a pet roly poly. I think I'm not sure if it's how it identifies, but
Still,
like
we'll have to meet again for you to give me guidance. You've kind of told me the story, but you haven't told me how I do this. But okay, we'll keep that for
I don't
another
know.
time. But similar to you, my wife does make me try and feel that we are equal,
Yeah.
and then I ask my daughter, "Who's the real boss?" Mom. You know, so
I don't
she
know. I
knows.
don't
I
know.
know. You know.
I don't know how you do it. But I think it's something like that because just one thing going back to my sons, I do think that they see that. I've just heard them like talk about other friends, families, or whatever. I think there's something in that. Like I don't know how you architect it, but there's something in there that goes back to your family and your partnership with your partner that the kids see and they identify themselves in that. I think that's where the answer is. I don't know what it is. You need a
Yeah,
sociologist,
I
not an
think
engineer.
as a company, it's always the challenge becomes the balance, right? You need technical competence, but you also want diversity. and that's where the challenge is. But yeah, it's an ongoing challenge. But if you do think of something where we can get the right women on board somehow,
Yeah.
will be great, because we were almost 50-50 in our leadership team, and now it's literally like 80-20 again. So so but that's okay. We'll figure it out so, slowly and surely. Okay, so I'm coming to the closing time, but I'm happy to hear if there are things you want to talk about. But the one thing that I want to go towards is, what's the dream? So if you were to look in a crystal gazing ball and see the future 5 years hence, and there were no barriers at all for you in terms of money, in terms of talent, in terms of technology, what would it look like? What would Mango Materials look like? And what would you have achieved? What would that dream look like?
It would look like billions and billions of pounds of PHA produced from methane all over the world. So it would be production facilities. And then not only that, if we're talking like 10 or 20 years in the future, you could use our technology in deep space because there's methane there. So the big long-term dream would be that PHA is the main type of polymer material being used in our everyday lives for any kind of like disposable type application. So, and like as part of that journey, I'm seeing it everywhere, like out on the streets. It's used for packaging. It's used for all food packaging, cutlery, like any kind of plastic bag. We take all our organic food waste. We take all our PHA. We put it all in a single bag. We take that bag. We put it back to the anaerobic digester, thrash it up, produce methane to make, PHA, but also to make electricity, to make fuel, sure, heating, like I think we mentioned at some point in this call, use methane for all of that. We have a C1 platform, make those materials locally, use the carbon locally all over the world, have these resilient communities that are making their materials on demand, going methane to PHA. That would be the billions and billions of pounds, dollars dream.
Definitely more power to you. And I'm sure Elon Musk would be so happy to hear that you're going to produce PHA in the outer space too. Anything else, Molly, that I might have missed and you want to add about Mango Materials, about your journey, about the way forward?
No, I mean, I think that covers it. Like, I mean, I think I feel just enormously privileged to be able to do something that I love and that I'm passionate about, and to do it with people that I really care about. Um, and I know, like, and at the same time, it can also be really stressful and a lot of pressure, and you need more money, and you need more people, and you need more material, and you need more customers, and you need more time, and so all that can also be stressful. For me, it's a perfect match, and so for anyone else who thinks they see their thread and thinks they could be that too, I firmly believe that anything you might be lacking, you can learn and figure out. And then for certain people, that would just be, oh my God, this would be anxiety provoking. Then the world needs other members of the team that have sort of more stable long-term outlooks than because being on a startup company, it is fun, but it is a roller coaster, and there's ups and downs, and you need to be able to stomach that and just kind of stay steady. So that's what I love about it, but I would just want to share that in closing.
Yeah, I like the idea of a perfect match with your personality, and it reminded me of my father, because if somebody would come to him and say, we have a big problem, and this is something that's happening, what are we going to do? You would just look at them and smile and say, thank goodness we have a problem. We have a job because we have a problem. We have something to do.
I love that.
Okay, my final question. What does good garbage mean to you?
Well, I believe landfills and waste are the gold mines of the future. So, good garbage to me means keeping carbon always in play.
Succinct and deep. Thank you. So it has been such a joy, Molly, to chat with you, to feel your energy more than anything else, just the joyousness around what you're doing and life in general. Thank you so much for doing what you're doing. And I do look forward to a future which is methane led and PHA packaged. So thank you again for taking the time and being on the show.
Wonderful. Thank you so much for having me.